I'm just getting back to where we left off. Chapter 15 is kind of a catch-all chapter when it comes to urine and body fluids. So we've figured out how urine is made. We talked about glomerular filtration rate, renal filtration, and now we're going to, my computer helps me out here, start talking about various body fluids and how our body maintains proper fluid levels in general. So, of course, you should know at this point that water is the majority of our body. 45 to 75% of our entire body mass, depending on age, gender, and fitness, is water. The body fluids are divided into three major compartments. You have your intracellular fluid, which is the fluid within the cell. That's the majority of our body fluid is found within those cells. 2/3 of our body fluids is within the cells. Then you have your extracellular fluid, which is outside of the cell. And this could either be the fluid in between the cells and tissues or the blood plasma. So when we're talking about extracellular fluid, we're either talking about interstitial fluid or blood plasma, which is the fluid around the blood cells. So in general, looking at our total body composition here, you see females about 55% fluids, males, because they have higher muscle composition in general, have higher fluid. So around 60% of that total body fluid, 2/3 of it is inside the cells, 1/3 of it is outside of the cells. Most of it is that interstitial fluid or cell juice, as I like to say, that kind of fluid surrounding all of our cells. And then the blood plasma makes up a small percentage of that as well. So how does it travel? Fluids are exchanged in between cells, surrounding interstitial fluid, and this is all because those cells have selectively permeable membranes. We talked about this way back in chapter 3, I believe. The fluid can be exchanged between the fluid plasma, or the blood plasma rather, in the capillaries and the interstitial fluid, again, because the capillaries have that simple squamous lining that allows for diffusion very easily. The fluid exchange is continuous at all times. Fluid is being kind of fine-tuned inside and outside of cells, and that's all to maintain homeostasis. So when water and solutes are in the right proportions in the fluid compartments, that's when equilibrium or homeostasis is reached. This animation here goes through water and fluid flow. Let's talk about electrolytes. You may have heard of electrolytes before in just general everyday medical terminology. An electrolyte is a compound that separates into ions and conducts electricity. So some of the big ones in our body are sodium, chloride, and potassium. They're going to control the osmosis of water in between the fluid compartments inside and outside the cells. There's also hydrogen and bicarbonate, which are going to help maintain acid-base balance. Sodium, potassium, and calcium are going to carry electrical currents for action potentials, and calcium, magnesium are going to be cofactors for enzymes, or special helpers for enzymes, getting them to work a little better than they would without them. So the majority of our electrolytes in our body are within our blood plasma. You see here, sodium is in high concentration in our blood plasma as well as interstitial fluid. Potassium, you may recall, is high concentrations inside the cells in the intracellular fluid. Chloride, here's another one, high concentrations in the blood as well as the interstitial fluid, very low intracellular fluid. Our phosphate, our organic phosphate, is mostly inside of our cells. This is with ATP. So our cells need that organic phosphate to be available. You don't have to have these numbers memorized. This is more for reference than for memorization terms. So let's talk about how osmosis is controlled in the body. It's controlled by the osmotic gradient. The movement of water is regulated by that distribution of electrolytes between the plasma, interstitial fluid, and intracellular fluid. When I say plasma, I mean the fluid portion of the blood. Sodium is accounting for almost 50% of that osmotic pressure of the extracellular fluid. So in other words, the amount of sodium in our extracellular fluid is really going to play a huge role in how water moves throughout our body. And you may know that already just from everyday life. You eat a really salty meal and the next day you notice you're retaining a little bit of water. and that's because sodium is affecting your osmotic pressure. There's also chloride. The balances of the chloride ions are going to help to balance the intra and extracellular compartments of our cells. So, we've talked about our kidneys. The kidneys are the main mechanism for controlling osmotic pressure inside of our body. It's going to help excrete any extra water by diluting the urine, or excrete excess electrolytes by concentrating the urine. And therefore, our kidneys are integral in maintaining blood pressure. Changes in water levels are going to change blood volume, and because our blood volume changes, so does blood pressure. Let's talk about water intake. Homeostasis is maintained by that equal gain as well as loss of water. It's about 2,500 milliliters a day, or 2.5 liters of water a day, which is what they say. About 3 liters of water a day is what they recommend. Water is taken into the body in 3 ways. Drinking, that's the obvious one. Eating foods that contain water. Some of us take for granted the fluid concentration of the foods that we eat. Something like iceberg lettuce has a very high water concentration, where something like peanuts has a very low water concentration. As well as chemical reactions. The actual process of digestion releases water into the body. Water is lost from the body in a number of different ways. It's not just excreted through urine. Of course, from the kidneys, that would be urine creation. There's also evaporation from the skin surface, that sensible and insensible perspiration. You're losing water right now through your skin, and you probably don't even know it unless you're sweating. The exhalation from the lungs. You may be aware that when you exhale, there's a number of fluid droplets that come out when you are exhaling. There's also water in your feces. Women, when they menstruate, are losing water as well. So, a number of different ways water is lost from the body. It's essential that you're bringing water in to make up that difference. Our daily water balance, again, some of it is metabolic water produced from our chemical reactions. Some of it comes from our food. The majority of it, of course, is coming in from the liquids that we drink. How do we get rid of it? The majority of it through our urine, a little bit through our skin, a little bit through our lungs, and even less from our feces. Dehydration is when water loss is greater than water gain. This could be because of exercise, working in a hot environment, not drinking enough water, vomiting, diarrhea. Anything that's going to cause an excess of water loss can cause dehydration. There are special Osmo receptors that are located within the hypothalamus of your brain. These are going to sense fluid level changes in your blood plasma, and that's going to stimulate that release of ADH from your posterior pituitary. You may remember that ADH is antidiuretic hormone. What is it going to do? It's going to stimulate that reabsorption of water in the kidney, and it's going to help that kidney produce a very concentrated urine. In other words, getting the water back from the filtrate, getting it back into your blood plasma. It's also going to stimulate you to drink more fluids. It's going to activate your thirst centers. ADH also makes the distal convoluted tubules and collecting ducts permeable to water for reabsorption. So the kidneys' role in water reabsorption, you can see up here. There's some type of stimulus causing a decrease in blood water concentration. In other words, you have a low blood volume of water. So those osmo receptors in the hypothalamus say, uh-oh, we need to up our water. So that's going to cause the release of ADH, causing the change in permeability in the distal convoluted tubule, as well as activating thirst centers, increasing our blood water concentrations, getting us back to homeostasis. There's also the renin, angiotensin, aldosterone system. Basically, the cells within the afferent arteriole are going to sense dehydration and release the enzyme called renin. Renin is going to trigger angiotensin 2 to be created. That is going to trigger the secretion of aldosterone from the adrenal glands. Aldosterone increases sodium reabsorption and therefore water reabsorption, because water follows salt. So ultimately, this is going to help reestablish our blood volume and blood pressure as well. ANP, atrionatriuretic peptide, is another hormone that this one's released by the heart, and this is released when blood volume and blood pressure are too high because of excessive fluid intake or excessive salt consumption. So it's going to act on the kidneys to cause the kidneys to excrete more water and more sodium. Here's the sequence of the angiotensin-aldosterone system. You see our afferent arteriole here, sensing that high blood pressure, or rather low blood pressure, I should say, and that's sensed by these special juxtaglomerular cells right here. That's going to stimulate the release of renin. And you see this process here. The liver makes angiotensinogen. Angiotensinogen is going to be converted by renin to angiotensin 1. Angiotensin 1 floats in the blood up to the lungs, where it meets up with another enzyme called ACE, angiotensin converting enzyme. Angiotensin converting enzyme converts angiotensin 1 into angiotensin 2. Angiotensin 2 stimulates the secretion of aldosterone from the adrenal glands. Aldosterone is going to stimulate the reabsorption of sodium and therefore the reabsorption of water at the kidneys, so you're going to get a increased blood volume, ultimately restoring blood pressure. Individuals that take high blood pressure medication are probably taking an ACE inhibitor, and you can imagine this chain of events being stopped right here at the lungs, so that angiotensin 1, that's a typo there, it's not angio, it should be angio, that angiotensin 1 is not converted into angiotensin 2, therefore aldosterone is not being released in instances where people are taking an ACE inhibitor. The urinary calculi, or is another name for kidney stones or bladder stones. This is when the concentrated urine is produced, calcium, phosphorus. It's going to crystallize out of the solution to form stones. It's the increased likelihood if there is an alkaline pH and urinary tract infections. It's treated by an acidifier or by breaking those stones into smaller pieces using ultrasounds or lasers. They'll eventually pass naturally through the tubing, although if you know anyone that has ever had them, it seems like a very unnatural process because it is very painful. They can be prevented by consuming adequate amounts of fluids, as well as reducing the intake of certain foods that promote the release of minerals into the urine, like those alkaline producing substances. So let's talk about homeostatic pH and how is it maintained. Ultimately, we have buffer systems in the body, in our blood specifically, as well as intracellular compartments to help balance any acid or base imbalance that we may have. Exhaling carbon dioxide is one way, and there's also kidney excretion being another way to maintain a level of pH in our body. Let's take a look at some of the buffer systems here. There's 3 different buffer systems. There's a protein buffer system, a carbonic acid bicarbonate buffer system, and a phosphate buffer system. The one that you should probably know the most about, or really the most important one, is this guy right here, this carbonic acid bicarbonate buffer system. We talked about this briefly when we talked about the respiratory system. You may recall that the majority of carbon dioxide that's released from our cells after cellular respiration goes into the blood and is converted by carbonic anhydrase into carbonic acid. Carbonic acid dissociates into a hydrogen ion and a bicarbonate ion. When pH rises, in other words, when there's too many hydrogen ions, the opposite reaction will form. In other words, hydrogen will rebind to the bicarbonate ion to form carbonic acid. When the pH drops, then the reverse is going to form, and you'll have a release of hydrogen ions into the solution. So this is kind of a him and a haw between bicarbonate and carbonic acid to help maintain a proper blood pH. There's also a protein buffer system. This protein buffer system is simply where these amino acids will either reabsorb or release a hydrogen ion depending on the pH demands of the system. The phosphate buffer system is another simple system, the idea of a hydroxide ion and your phosphate acid here forming water and a monohydrogen phosphate, and then just going back and forth between these various components as a phosphate buffer system. Because phosphates are the major anions within the intracellular fluid, the phosphate buffer system is playing a major role inside the cells, whereas the bicarbonate carbonic acid cycle is really playing more of a role within the blood. There are states of our body that exist when low or high pH occurs. Acidosis is when the blood pH gets below 7.35, and alkalosis is when the blood pH exceeds 7.45. So as I mentioned, those major buffer systems, the protein buffer system is that most abundant in the intracellular fluid as well as the blood plasma. This is when hemoglobin, albumin releasing or combining with hydrogen ions to help maintain that pH. That carbonic acid bicarbonate buffer is when there's a give and take between the bicarbonate and carbonic acid between the lungs and the kidneys within the blood to maintain homeostasis. The phosphate buffers are a very important buffer in the urine, regulating the cytosol pH as well, similar to that carbonic acid bicarbonate buffer in that it gives and takes those hydrogen ions. This animation here goes to the regulation of pH in the body. So let's talk a little bit more about that important one that I like to think of as the most important, our carbonic acid and bicarbonate system. Ultimately, increasing the rate and depth of breathing. So think about that. The more you breathe and the deeper you breathe, that's going to cause your carbon dioxide concentration to lower. You're exhaling lots and lots of carbon dioxide. It's also going to lower the amount of hydrogen ions in your body. It's going to increase your pH. As you're getting rid of that carbon dioxide, you're getting rid of your bicarbonate, and therefore you're getting rid of that carbonic acid, which is going to decrease the pH of your blood. Decreasing the rate and depth of breathing, taking low, slow breaths, is going to increase your hydrogen concentration, increase your carbon dioxide concentration, and lower your pH, make your pH more acidic. So the rate of breathing is actually detected by your chemoreceptors within the carotid artery, within your aorta, and within the medulla oblongata. And so those respiratory mechanisms can respond to changes in blood pH by altering your rate and depth of breathing, and therefore altering the carbonic acid concentration in your body. The carbonic acid bicarbonate system in the kidneys is going to permanently remove any excess hydrogen ions or bicarbonate ions from the body. It can also alter the reabsorption of hydrogen or bicarbonate. That renal mechanism can take up to hours or days to remove that excess hydrogen ions, but it is permanent. Once the hydrogen's gone, it's gone. It takes a while to reestablish itself. Here's the drawing from your textbook. You have some type of decreasing blood pH. In other words, your blood pH is getting more acidic. You have an increase in hydrogen ion concentrations. It's going to signal to those chemoreceptors within the medulla, within the carotid and aortic bodies. Hey, we have a very acidic pH going on here, maybe a 7.30, 7.32. So your medulla oblongata is going to sense that and change your rate of breathing. Your diaphragm is going to contract more forcefully and more frequently. Your rate and depth of breathing is going to increase. So you're getting rid of more of that carbon dioxide. Less bicarbonate ions, going to form less hydrogen ions. The blood pH is then going to increase and go back to normal. Your hydrogen ion concentration is going to decrease. And then you get back to homeostasis. When we're talking about the interplay between kidneys and lungs, by altering the rate and depth of breathing, the lungs alter that carbon dioxide concentration, so shifting the equilibrium from the carbonic acid bicarbonate. It's going to alter the blood pH. That's a respiratory mechanism, and it's very powerful. It can respond within minutes. The kidneys are going to alter the reabsorption or secretion of hydrogen or bicarbonate by shifting the equilibrium of that carbonic acid bicarbonate buffer by literally removing the hydrogen or bicarbonate or by adding it back. So this is a much slower mechanism within hours or within days than that respiratory mechanism. And that is the end of chapter 15.